Welcome to our discussion on linear programming, graphical methods. And our objective here is to use some graphical methods to find the optimal value of a linear function that is subject to constraints. Basically, we're trying to maximize profits and things like that. So the first thing we have to figure out are what are called feasible regions and solutions. Many of our practical problems in business and economics want to optimize something, some function, such as cost or profit. And we always want to optimize that, maximize it, subject to some sort of complex relationships amongst your capital, your raw materials, your labor, your costs, right? All sorts of things. So here's a typical example. We've got a farm co-op has 6,000 acres available in which to plant corn and soybeans. The following table summarizes each crop's requirements for fertilizer, herbicide, harvesting labor hours, and the available amounts of these resources. So you can see that how much area they have for fertilizer, herbicide, right? For corn, they need 9 gallons per acre. For soybeans, 3 gallons per acre, and they have 4,500 gallons to use, right? So it's a limited resource. They only have so much fertilizer, herbicide, and different crops use different amounts. They also have labor to harvest the crops. It takes 3/4 of an hour to harvest an acre of corn. It takes an hour to harvest an acre of soybeans, and they only have 5,250 total hours to do the job. So based on those constraints, they want to try and maximize their yields, right? Maximize their profits if they know that they make $240 per acre for corn and $160 per acre for soybeans. So let's see how we'd work through this. We could use linear programming to determine the area, right, the feasible regions, the solution area for all of these constraints, and then see which critical values are going to maximize the function. So all these limitations on these variables, we call them constraints, and we can express them as linear inequalities. And the function that we're trying to maximize or minimize, we call that the objective function, and it's also a linear function. And when all of that's true, because it doesn't have to be a linear function, when it's a linear function, the problem is called a linear programming problem. So linear programming is widely used in business to try and solve these types of things when you have many variables, so sometimes far more than 100. We're obviously just looking at some basic ones with two variables. We can have more than 2 constraints, but usually just a couple constraints. So in this section, we're going to begin the study of this important topic by considering problems that just have 2 variables, and they can be solved with graphical methods. The constraints are going to form a system of linear inequalities in these 2 variables, and the solution determines a region, and then any point that can yield the optimum, maximum, or minimum value for the objective function is going to be in that region. And we're going to learn very quickly that those points actually land in very specific places. So any point in the region determined by the constraints is called a feasible solution. The region itself is called the feasible region. And in linear programming problem, we want to seek the feasible solution that therefore maximizes or minimizes our objective function. Because sometimes we want to minimize, like for instance, if we had a bunch of stuff and then it was dealing with cost, we'd want to minimize our cost function. So here is the feasible region as an example for a closed and bounded region. And the reason why we call it closed and bounded is you can see that there are lines all around the blue area. The blue area is the feasible region, and it's trapped. And the reason why it's trapped is when we have our variables that are representing something like hours of labor or gallons of pesticide. Basically, anytime we're working with real-world examples, our variables are always going to be constrained to being greater than or equal to 0. So we're always going to be working in the first quadrant only. So the y-axis and the x-axis will always act as constraints, because it makes sense that you can't have negative of these things, right? You can't have negative hours of labor. You can't have negative gallons of pesticide, those types of things. Now, the solutions to these linear programming problems. When a feasible region for a linear programming problem is closed and bounded, like the previous picture, the objective function has a maximum value and a minimum value. When the feasible region is not closed and bounded, the objective function may have a maximum only, a minimum only, or no solution whatsoever. So it's kind of nice when it's bounded, closed and bounded, we know that it has both a max and a min. However, when it's open, unbounded, it could be that it doesn't have either or it only has one of them. If your linear programming problem has a solution, then that optimal value, that minimum or the maximum value of the objective function always occurs at one of the corners of the feasible region that is determined by the constraints. So that's what I was talking about before, where we know those critical values is what I call them, the things that make your objective function a max or a minimum, always occur at the corners where things intersect. If your objective function has its optimal value at two corners, then it also has that optimum value at any point on the line that connects those two corners. So for instance, if this point 0, 10 and this point 10, 8 both maximized your objective function, then this entire line x plus 5, y equals 50 would maximize that function. And then same thing if 10, 8 and 14, 0 maximized or minimized your function, if that's what you're trying to do, then this entire line, 2x plus y equals 28, would therefore maximize or minimize your function. But we do know that these 3 points are going to be your only choices for maximums and minimums. Technically, 0, 0 is always a point, but it's a trivial point because it means you're not doing anything, right? So you could obviously minimize cost by not doing anything, but then you're also not going to make any profits. So it's a trivial thing that we don't normally look at. It's just the ones that we get from the other intersections, right, where the lines are crossing the x-axis, where the lines are crossing each other. Okay, so let's look at our example. The steps that we need to do to solve these things. First, we need to find the optimum value of a function subject to those constraints. In this case, we want to maximize and minimize values of c equals 2x plus 3y subject to these constraints. And those constraints are just those technically two equations, and then, as I said, your variables are always set greater than or equal to 0. So the first thing you do is you write the objective function and constraints as inequalities. So there's our objective function, there's our constraints. Then the next thing you do is you graph everything. You graph the solution of the constraint system by basically graphing all of the lines and all the constraints, right? Not the one you're trying to maximize or minimize. So you graph all the constraints and then find the feasible region. And if it's closed, we proceed to step 3. If it's not closed and bounded, we check whether an optimal value exists. If not, we state this, and if so, proceed to step 3. And by checking it, it's basically you take the corners, right? So we've constructed it. We find all the corners. There's the trivial one, 0, 0. Here's 7, 0, 0, 5, and then this intersection here happens at 6, 2. Since this one is closed, we know we can go to step 3, where we find the corners, and finding this one means we have to solve the system of equations, those two equations simultaneously by whatever method you prefer. Once we've done that, we evaluate all of those points in our objective function. Simply just plug them in and see what we get. We can see that this one here maximizes our function at 18. This one here minimizes it at 0, but that might be a trivial minimization, so we might go with this one instead, depending on the context of the question. So in terms of just the raw results, it's maximized at the point 6, 2, and we get a maximum value of 18. It's minimized at the point 0, 0, and we get a minimum value of 0. So let's go back to our farm example. So if market conditions change so that the co-op's profits per acre change to 300 and 100, how should the co-op adjust its planning to maximize profit? Well, here's our new profit, or is that the old one? 240. That's the old one. So here's the old one. So here's our profit function that we're going to try and maximize. Here are our constraints. And then, of course, our values are always greater than or equal to 0. We graph everything. And with the 3 lines, we get all sorts of weird graphing. This little tiny triangle piece in there, you can see that's not part of the solution. Even though these 2 lines cross out here, this line in here, which is shaded to the inside, overlaps this stuff. So it becomes this weird shape here with that point, that point, that point, that point, and then, of course, 0, 0. Here's all of the points that we found. Plug them all into the profit equation. We can see that this one maximizes it. So we get maximum profits when x equals 3750 and y equals 2250. That means the co-op plants 3,750 acres of corn, 2,250 acres of soybeans. Because remember, x and y were acres of each of the plants. And if it does that, it maximizes its profits at 1.26 million. Now, if the market conditions change for profit, but nothing else changes, right? Their constraints don't change. The nice thing is we don't have to worry about finding new numbers. We just slap them into the new profit function. So here are the same numbers put into the new profit function. And once again, we can see that profits are maximized with the same constraints, 3750, 2250. Now, please don't think that's always the case. It just so happened to work out this way. So we can see that from both examples, we know what to how much to plant in each crop. That's where prop came from, planting crops. And we know that that's going to maximize our profits. And then based on, which price model we're using, we're either getting 1.26, I think it was, million or 1.35 million. Okay, let's look at an example where we want to minimize things. So we want to find the maximum minimum values of this simple function subject to these constraints. We graph everything, and we see that we have a system that is unbounded. So that tells us that we could have a max, we could have a min, or we could have nothing. Now, our function, our thing that we're trying to, in this case, minimize or maximize, I think they want us to minimize, is a simple line of x plus y. This figure shows what happens, right? It shows the solution regions with graphs of c equals x plus y for c equals 3, 5, and 8. So basically, if you set x plus y equal to 3, you get this line, x plus y equals 5, you get this one, x plus y equals 8 gets this one, and you see that it'll just keep going out. These are parallel because they're the same line set equal to a different constant, so they have the same slope, right, same number in front of x. Note that the objective function has a minimum but no maximum. So we can see that it minimizes itself here when it hits that point. And as it goes out, it continues to exist, right? It can exist anywhere in the blue stuff, so it has no maximum. It just keeps going. So that's where our minimum would be at c equals 5, and that would be the point 2, 3. X would be 2, y would be 3, and that would minimize our cost at 5. We can see that the corners of 0, 6 and 11, 0, right? 0, 6, 11, 0, can be identified from the graph. The third corner, 2, 3, is found by solving the system of equations, right? So the best method I always think is the addition/elimination method, where you add things together so that one of the variables goes away, and then that gives you a simple solution to the one variable. Then you plug it back in to get the second one. So there's that 3, 2. And then if we examine the value of c at each corner point, put in 6, 0, we get 6. Put in 11, 0, we get 11. Put in 2, 3, we get 5. So there's our minimum. If we wanted to maximize it, of course, it doesn't technically maximize at 11 because that region goes on forever. So it basically says you just keep making x's and y's bigger and bigger and bigger, and you'll maximize that c function, whatever it happens to be. Okay, that's all I've got for you.